the topic that I have been covering called Introduction to Water Management. In the water management techniques, in the initial lectures, we have discussed about groundwater, surface water, their interactions, losing stream, gaining stream, and the different kind of streams like thermal streams, semi-permanent streams, and permanent streams. Right? These things we have discussed. Today we will go a step further in this topic, and we'll discuss about groundwater surface water interactions and how they can be quantified. Now, the first question that comes into mind while discussing this topic is why we need to quantify the groundwater surface water interaction. Right? So, as I told you in the previous lectures also, that groundwater surface water, they are always interacting with each other at a constant rate, right? Sometimes groundwater is supported by surface water, sometimes surface water is supported by groundwater. This is the way losing streams and gaining streams are there, and this is the way water tables are maintained, right? So the purpose for which this study is required is to know at a particular place groundwater or surface water how they are reacting. If it is being quantified, it will tell you at particular positions is it a gaining stream or losing stream of water, right? Interaction of groundwater surface water where the groundwater is supporting surface water and where surface water is getting supported by groundwater. In a particular area, suppose if you want to study a particular area where you want to know at which places the groundwater and surface water interaction are supporting each other, this will tell you what is the amount of water which is being supported from ground to surface or from surface to the ground, right? This is the significance of groundwater surface water interactions, right? So there are many different ways by which these quantifications can be done, right? There are different approaches to do these kind of quantifications. These approaches are categorized mostly into 5 categories. One of them is the analytical approach. Second is water balance approach. Third is hydrological approaches are there, numerical approaches are there, right? And tracer based approaches are there, right? 2 of them are very important, that is the analytical approach and tracer based approach, which are generally being used at the field level, right? Among these 5 approaches that I have written here, this analytical methods or approaches and numerical methods. These 2 can tell you about the groundwater surface water interaction, right? And its outcomes also, right? Its outcomes mean it predicts how an interaction can change over time. These 2 approaches can tell you how this groundwater surface water interaction can change over time, right? Can predict about it. But rest of the approaches like water balance method, tracer method, and hydrological method, these approaches tell you at a single point of time how the groundwater and surface water are interacting with each other. Right? Now the next question that comes is how do we do this kind of quantification of groundwater surface water interaction? Because water is a big body, it flows to a long range, right? How come we can quantify the interaction between groundwater and surface water? So to quantify these interactions, there are different properties which can be explored. One of them is water flux, right? Water flux means say hydraulic conductivity, right, between 2 layers, groundwater layer and surface water layer. That can be utilized. Then second approach which can be utilized is tracer based approach, right? Tracer based approaches. These can be utilized, right? Then there are some methods in which Darcy's law can be explored, which discusses about the seepage of the water, right? Flow of the water. Darcy's law basically discusses about the flow of the water. So basically these 3-4 approaches are there, 3-4 properties of the water, all the approaches are there by which these kind of quantifications can be done. The surface water, groundwater quantifications can be done. water flux tracer based methods and some methods based upon Darcy's law. One by one we will discuss them all. First of the approach in which measurement of water flux is done, it is done by a very simple instrument called seepage meter. Right? Seepage meter. Seepage meter basically it's a very simple, easy to make kind of instrument. Right? This has a collection bag and it has a flexible tubing and it has a piezometer connected to it. The piezometer basically it measures the hydraulic conductivity of both of the layers, groundwater layer and the surface water layer, and it compares it. Right? This is the basic idea about a seepage meter. It has a collection bag. Right? When there is a gaining stream, if these kind of seepage meters are kept in different locations in the water, suppose there is a gaining stream, water is going from the groundwater level to the surface water. The water will go from here, the groundwater layer, inside the collection bag layer. Right? Right? When it will go inside the collection bag, the piezometer will record the hydraulic conductivity and it will compare it to the surface water layer. Right? So this hydraulic conductivity is measured by piezometer. Now this hydraulic conductivity, it is basically a property of the water, right? Hydraulic conductivity is related to hydraulic head. Hydraulic conductivity is related to hydraulic head, right? Hydraulic head means a point in water column where maximum energy is there, energy of a particular water column at a point, right? Hydraulic head is a energy, whether it is kinetic energy or potential energy or accumulation of both, right? At a particular point in a water head. It is measured in meters or in height, right? So the hydraulic head conductivity or hydraulic conductivity of groundwater layer and surface water layer, they are different, right? When the water goes in a gaining stream, when the groundwater goes into the collection bag, you will find there is a difference between the groundwater conductivity, the groundwater hydraulic conductivity and surface water conductivity, right? This is the way water flux can be calculated, right? By a certain meter called piezometer, right? So this kind of simplistic way of measuring water flux by piezometer is the easiest approach available in this particular approach. Now this piezometer approach is very effective, right? It can be used to quantify the groundwater and surface water interaction, but not all the time this particular approach is useful, because it is assumed in this approach that all the groundwater, all the way it supports the surface water, but this is sometimes not true, because there is a hyporeach zone also, right? Which sometimes hyporeach zone is a zone between groundwater and surface water, right? It's basically the mixture of groundwater and surface water. Sometimes hyporeach zone also supports the surface water, right? And that cannot be measured by seepage meters, right? So this is the advantage of seepage meter. But as such, seepage meter calculation of water flux is most of the easiest way by which groundwater surface water interaction can be quantified. Another approach that is used for quantification of groundwater surface water interactions is tracer-based methods, right? Tracers are of different kinds. Normally here we are discussing a heat tracer, right? This basically, if I have to give you an idea about the tracer method by heat, right? Heat tracer method, the groundwater layer and surface water layer, they have different temperatures, and this temperature variation can be utilized in using it as a heat tracer, right? Heat based tracer method, in which we assume that groundwater layers, their temperature in the groundwater layer is more stable, right? And the surface water, because it is exposed to sunlight, to the evaporation, the temperature is higher, right? So it has slightly different temperatures. Surface water has different temperatures because it is exposed, right? And groundwater has a stable uniform temperature, right? So when there is a losing stream, suppose there is a losing stream and surface water is losing water to the groundwater, in that condition the surface water you will find variable sediments and variable temperature in surface water layer, because this water is going down, right? But when there is a gaining stream, the groundwater is coming to the surface water, you will find not much of temperature difference, not much of sediments different when there is a gaining stream, because groundwater layers, basically the temperature in the groundwater layers, because they are not exposed to the outer conditions, the gaining stream, in case of gaining stream, the groundwater when it comes up, the temperature doesn't change too much. But when there is a losing stream, when the surface water goes down to the groundwater, you can find the variable sediments as well as variable temperature conditions in the surface water, right? This difference between the temperature can be quantified by this particular method, in which when there is a temperature difference between the two layers, there becomes a temperature time series, right? When the downward water causes, when the water is in the losing stream, the surface water is losing the water, it creates a downward water, causes a deeper penetration to the cyclic temperature, right? And there develops a temperature envelope, right? Right? This particular temperature envelope tells you about it has different ranges of temperature. The different ranges of temperatures are measured in temperature envelope, right? Which has a maximum minimum temperature forms, right? This temperature envelope can be measured, right, by certain heat transport equations, right? These heat transport equations covers up advective heat transport and convective heat transport of the different layers, groundwater layer and surface water layer, right? So this method basically measures the difference between the two layer temperatures, groundwater layer temperatures as well as the surface water layer temperature. Groundwater layer temperatures, they are more stable because they are not exposed to the outer conditions. Surface water layer, they are because they are exposed to evaporation, they are exposed to higher temperatures, so they show variation. When there is a losing stream, the water comes down from the surface water to the groundwater, right? Then you will find a change in the sediment as well as in the temperature when there is a losing stream. But when there is a gaining stream, right, you will not find too much of difference because groundwater has a stable temperature, right? This temperature series, change in the temperatures are recorded in series. This makes a temperature envelope, and this can be calculated by a heat transport equation, right? This is the method that I explained here, is the heat tracer method. Apart from it, there are certain other tracers also which are used in tracer-based methods, which are normally some kind of isotopes, right? Some isotopes are also used. One of the mostly used isotopes in tracer methods is radon, right? Radon, right? Radon isotopes are used, right? Radon is a product of uranium radioactive decay, right? The radon's concentration in groundwater and surface layer waters are different, right? The radon concentration in groundwater layers are more because this layer, groundwater layer, interacts with the rocks and soils at the bottom, right? That is why the radon concentration is more in the groundwater layer, 2 or 3 times, or in fact 3 or 4 times higher in size as compared to the surface water. So when we are doing a quantification of groundwater surface water interaction by tracer methods or by hydrochemistry method, the radon isotopes are most of the time used in this particular method. Apart from radon, there is one more isotope called oxygen 18, right? Oxygen 18 isotopes, these are also used, and deuterium also. these are also used in tracer-based methods, right? Apart from it, chloride ion concentration and electrical conductance. Electrical conductance are also used in the tracer-based methods. So these tracer-based in these kind of hydrochemistry-based tracer-based methods, radon is maximum used because radon's concentration can easily be quantified. Apart from it, oxygen 18 isotope, because it is a component of the water, H2O, right? This can easily be measured. Deuterium also, because it's a isotope of hydrogen. Hydrogen is also present as an isotope in water. This can also be used as a tracer-based method. And apart from it, chloride ion, electric conductance, and sometimes alkalinity also can be used in the tracer-based methods. Third, the approach by which groundwater surface water interaction can be quantified is by Darcy's law. Darcy's law is it basically tells you about the flow of a water in a particular water column, right? Darcy's law says that Q, that is a specific discharge at a particular point, is equal to minus K into dH upon dL, right? Where K is hydraulic conductivity and dH upon dL is hydraulic gradient, right? dH is hydraulic head, dH is hydraulic head, and it's the dL is the length, right? Length between two hydraulic heads, right? In the seepage meter, when I was discussing the seepage meter, I told you that seepage meter calculates the difference between the hydraulic head. From a high hydraulic head, water flows to the low point hydraulic head, right? So when hydraulic head difference, there is a hydraulic head difference between two layers, groundwater layer and surface water layer. That can be calculated by dH upon dL. That is called the hydraulic gradient, right? Hydraulic gradient is the difference between two hydraulic heads between a particular length. If there is two hydraulic heads are there, one is in groundwater, one is in surface water, right? They are at different positions, right? These two different hydraulic heads at how much distance they are available, right? That can be calculated, and that will be called the hydraulic gradient. So the Darcy's law says that specific discharge from a particular point is equal to minus K, that is hydraulic conductivity, the ability property of a soil by which the ease of water conduction through pore spaces are there in that particular soil, into dH upon dL, that is hydraulic gradient, right? By this way, many groundwater surface water interactions can be done. Some of the tracers method also uses the Darcy's law for the quantification of groundwater and surface water interactions. Okay, so the different approaches or the ways by which I have discussed the groundwater surface water quantification methods, they are mostly used in different approaches utilized these days to quantify these interactions, right? So if I say in the initial part of the lecture, I told you that there are majorly 5 different categories of groundwater surface water interaction quantification, which are analytical method, tracer-based, field and tracer-based methods, then water balance method, numerical methods, and hydrological methods. These 5 approaches, some way or another, they take the advantage of the methods that we have discussed in these previous part of the lecture. That is, sometimes Darcy's law can be advantageous, sometimes water balance equation is important, sometimes hydraulic gradient could be a good advantageous technique by which the groundwater surface water interaction can be quantified, right? So like the first approach which I discussed, analytical approach, it tells there is a relationship between the stream bed and the groundwater aquifers, right? If stream bed is in close contact with the aquifer, right, then you can easily tell the relationship between groundwater abstraction, the pumping from the groundwater, and the stream getting low. Like this particular approach, analytical methods or analytical approach, they can easily tell you if the stream bed is in close contact with the aquifer, and if you are taking in that particular area, you are taking the water out by pumps, right? Then this approach can easily tell you that the amount of water you are taking from the ground level, what effect it will have on the streams, right? This particular approach directly estimates the groundwater interactions. It applies when there is a hydraulic connection between the groundwater layer and the surface water layer, right? Hydraulic connection is very important. For this approach, there should be a equal full connection between the groundwater layer and surface water layer for this approach to be successful, right? And it applies when the stream fully penetrates the aquifer, right? Aquifer is fully penetrated by the streams, right? And apart from that, the water should be at the stable stage. Neither the gaining stream should be there nor the losing stream should be there, right? So when the water table is flat, that is neither a gaining stream nor a losing stream, then this particular approach, analytical method, is effective, right? And it can tell you that how much water you are boring from the ground, right? In proportion to this, how much of the stream flow will go down year by year or season by season, right? This is the basic idea about analytical method. Apart from that, other method, second method was that I discussed was water balance method, right? Second approach that I told you, which is important, is water balance approach, right? So in water balance approach, this is basically dependent upon say water balance equation. Like in a particular area, in a particular basin, whatever water is coming in form of rain, right, it should either be converted into stream flow, right, or it should be absorbed by the groundwater, right, or any form of water that is being lost also, like evaporation. Like if I have to write a water balance equation, it is P is equal to R plus E plus delta S, right? P here is precipitation, right? So in a particular closed basin, closed basin means a particular area where this basin is not contributing water to the other basin. It's a local basin, right? It is not a regional basin. So in a particular closed, isolated local basin, if rain is happening, it should be in form of either stream flow, runoff, or it should be evaporated. It should be evaporated on the top, right? Or it should be stored in the ground, right? Stored water in soil or in groundwater, right? So basically, water balance approach is based upon water balance equation idea, that is in a closed basin. Remember, this is the foremost criteria for this approach to be successful. In a closed basin, right? A basin where water is coming, but it is not contributing to the another basin, right? A local basin, right? So in a closed isolated basin, if rain precipitation is occurring, it should be converted either into the stream flow or total amount of water, the precipitation that is happening in a particular area, it is equal to stream flow plus evaporated water from that area, or it should be stored down into the groundwater layers or into the soil. So water that is coming into a system, it should be into these three forms: either stream flow, evaporation of water, and water stored in the ground or soil level, right? All these three forms, if you calculate all of them, then it will become total precipitation of the water. That means that water that comes to a system, it should not be converted to any other form but these three forms: stream flow, evaporation, and stored in the ground. So this water balance approach is based upon the same principle. It says that in a particular catchment area, if you are quantifying groundwater surface water interaction, that area, whatever water is coming, right? Whatever water is coming, it should either be converted into the stream flow or it should go to the groundwater. Now, when the water is coming into the system, right? When the water is coming into the system, either whatever water is coming inflow, right? And whatever water is going from the system outflow, right? And the whatever water is absorbed by the ground. These three measures can tell you exactly how much amount of water is getting absorbed by the groundwater. Inflow water minus outflow water, right? Inflow water in the system in a catchment and outflow water from the system, right? If you calculate minus the from inflow water, you minus the outflow water, you will get an idea how much amount of water is getting absorbed into the inside the ground, right? Water coming in flow of water minus outflow of water, right, is equal to water absorbed by ground, right, or soil, ground. Basically, this is the idea about this equation, that it says in a particular catchment, if a water is coming in form of inflow, if you calculate the inflow water minus it from the outflow water which is going away from the system, right, it will give you an idea how much water is absorbed by the soil or ground there, right? But very important thing to consider here is the evaporated water also. Evaporation process in which the water is going into the atmosphere, that should also be taken into account and that should be added here, right? Evaporated water. Evaporated water, right? So, water is absorbed in form of groundwater plus evaporation water. Is the water loss from the inflow of the water. Inflow of the water minus outflow of the water is equal to water absorbed by groundwater plus this consideration, that is some water has also been evaporated. Practically, this approach is it looks very simple, but this is practically not very applicable, because you cannot properly or precisely calculate the amount of water that is being inflowing, right? Amount of water that is being getting out, right? And amount of water that is getting absorbed by the ground, or amount of water that is being evaporated, right? So this catchment area where you are calculating the groundwater surface water interaction, they are sometimes divided into short sub-catchments, right? Sub-catchment area. Sub-catchment area, right? So small sub-catchment areas are made. One small sub-catchment area, then one more here, right? And plus one more here, like this. In a particular area, small sub-catchment areas are made, and and they are cumulatively studied to study about a particular catchment area where inflow of water is happening and how much amount of water is getting lost from there, right? This is the basic idea about water balance approach, in which it is said that water that comes into a system, it cannot get vanished, right? In some form it is there, right? Whether it is evaporated form or whether it is absorbed by the ground, right? So inflow of water minus outflow of water is equal to water absorbed by ground with evaporated water, right? This also should be considered for water balance approach. Apart from it, field-based methods I have discussed with you. Field-based and tracer methods I have discussed with you, like mostly heat, temperature of different surface layer and groundwater layers can be utilized for heat-based or tracer-based methods. Darcy's law again is utilized in many tracer-based methods. Application of different radioactive molecules like radon, and isotope tracing like deuterium and oxygen 18. These can also be used, right? These are the different ways by which these groundwater surface water interactions can be done. Apart from that, there is numerical approach also. Numerical approach, there is a simulation of groundwater and surface water layer interaction, right? So there is a model is developed based upon numerical approach. Numerical approach, right? In numerical approach, there is a model called mode flow. Mode flow is a model which kind of simulates the groundwater and surface water layer interactions, right? So, as I told you in the initial stage of the lecture, that different categories of approaches are there which can be applied to quantify groundwater and surface water interaction, but none of them single-handedly can be effective, right? So, one approach can take help from the other approach, like an analytical method approach. It can take support from the tracer-based methods, like or water balance approaches. They can take help from the analytical approaches, right? Two approaches in combinations can be utilized for effective quantification of groundwater surface water interactions, right? So in this particular lecture, I discussed the basic concept of what basically groundwater surface water is, how do they interact, and what are the different methods or approaches by which these interactions are quantified, like tracer-based methods, use of isotope tracing, then what is the use of hydraulic gradients, right? Piezometer, seepage water, seepage meter calculation of these groundwater surface water interaction. These things I have discussed in the lecture. I hope this lecture is beneficial for you.